Hello there, students. In this video, we're going to work through an example where a cannon launches a projectile that lands below the firing height. And we're going to see how fast an object needs to be moving in order to orbit the Earth at the surface. Let's start with the cannon example. Here we have a cannon elevated some height, delta y, above a flat plane. The cannon is shooting at an angle theta above the x-axis with an initial velocity of v0. The projectile will land at some distance, its firing range r, or delta x, downrange. We label our Cartesian coordinate system with x and y axes. Starting with some kinematic equations, knowing that there is no acceleration in the x direction, we find delta x is equal to v0 x times t. For the y direction, since we've chosen our y coordinate to be up, gravity becomes negative since it is pointing down towards the Earth. We find delta y is equal to v0 y times t minus 1/2 g times t squared. We can rearrange this to get everything on one side and then simplify the coefficient in front of the t squared so we can easily use the quadratic formula here to solve for solutions of t, the time variable. If we let the initial velocity, v0, be a reasonable cannonball velocity of 36 meters per second, or close to 80 miles per hour, and theta to be 30 degrees, and delta y to be a magnitude of 10 meters, we can plug all of this in and see what our possible solutions are for the flight time t. We also need to break down the initial velocity, v0, into its components, v0x and v0y. After plugging all of this in, we get two solutions from our quadratic equation. T equals 2.98 seconds, or t equals 0.68 seconds. Both are positive values, so we can't immediately rule one out as unreasonable, so which is our answer? We could plug in each result into a kinematic equation for delta y, and see which one gives us the correct vertical displacement of negative 10 meters. Remember, it's negative because the final position is lower than the initial position. If we plug in the result t equals 0.68 seconds, we find a result of delta y equals 10 meters. This should come as no surprise, since this is an input we use when solving the quadratic equation, from which the time variable we just used came from. But what did we just show? What does this time of 0.68 seconds mean in our problem? This is actually the time it takes to reach a height of positive 10 meters above the cannon before it falls back down. The other solution, t equals 2.98 seconds, is the point in time that the vertical displacement is equal to negative 10 meters, or when it impacts at the extent of its range. So now that we've seen a projectile problem with a range that doesn't land at the same height as it was launched, let's turn to the more complicated problem of how things stay in orbit. As always, we start with a diagram. Here is the Earth, showing the curvature of the surface, our cannon pointing directly tangent to the surface. We label a coordinate system with the familiar x and y axes. Here, our initial velocity is entirely in the x direction, tangent to the surface of the Earth. Gravity works entirely in the negative y direction towards the center of the Earth. The requirement to be in orbit is that an object must be moving fast enough such that the height it falls due to gravity, delta y, is equal to the change in height due to the curvature of the Earth separating away from the object, h. I also label the horizontal distance traveled here as d. The velocity in the x direction at any given time is just the initial velocity we started with, v0. The velocity in the y direction, using a kinematic equation, is negative g times t, since we have no initial y velocity, v0y. Looking at the kinematic equations that deal with displacements, we see that delta x is equal to v0 times t, and that delta y is equal to negative 1/2 g times t squared. Let's take a closer look at our Earth diagram to see what's going on here. Let's drop a label for the radius of the Earth, r sub e. The projectile will move that horizontal distance d, and the curvature of the Earth moves away over that distance by a vertical distance h. As measured from the center of the Earth, there is a small angle psi relating the initial and final point of the projectile in orbit. If we make a rectangle out of the lengths d and h like this, we now have one side of a right triangle with the length of the radius of Earth minus h, another side with the length of d, and the hypotenuse with the length of the whole radius of Earth connected with the angle psi. From this diagram, we can write the sine and cosine of the angle psi. From this, we can find the length d is equal to the radius of Earth times the sine of psi. And the length h is the radius of Earth times 1 minus the cosine of psi. For a small period of time t, we expect a very small angle psi, so we can use a small angle approximation for sine and cosine. If we only kept the first order terms of psi, or where psi appears in these sine and cosine power expansions to the first power, we see that there are none in the cosine expansion. The only term we'd have then is cosine of psi is approximately equal to 1 for small psi. But this would make our length h equation read h equals 0, which doesn't help us at all, since we know that the Earth is curved and it must fall away some non-zero amount over that distance d. To remedy this, we instead take the expansion keeping up to second order terms, or any power of psi up to psi squared. Doing so, we have sine of psi is equivalent to psi itself, and the cosine of psi is equivalent to 1 minus psi squared divided by 2 factorial, which is just 2. Plugging these approximations in, we have d is equal to the radius of Earth r sub e times psi, and h is equal to the radius of Earth r sub e times psi squared divided by 2. Now, for this projectile to actually be in an orbit, we need the distance d to be equal to the distance the projectile has traveled, delta x. And we need the distance the surface of the Earth has moved away from the object h to be equal to the distance the object has fallen, negative delta y. Again, don't forget the negative sign there. With these equalities made, we can rearrange the first equation to solve for the angle psi, then substitute that into the second equation. Doing that and simplifying, then solving for the initial velocity v0, we see that the velocity required to be in orbit at the surface of the Earth is simply given by v0 is equal to the square root of g times the radius of Earth, r sub e. Looking up the radius of the Earth to find it is equal to 6.37 times 10 to the 6 meters, and plugging in gravity as 9.81 meters per second squared, we end up with a required initial velocity of plus or minus 7.91 times 10 to the third meters per second. This is roughly 17,700 miles per hour. For reference, here are a few common speeds of objects we usually think of as being fast. And just to show the accuracy of our approximations, the actual velocity of the space station in low Earth orbit is also listed here at 17,200 miles per hour, just 500 miles off what we calculated. That wraps up this video where we learned a bit more about tricky projectile motion examples. Thanks for watching and learning about physics. If you have any questions or want to see a specific topic covered, leave a comment below or head over to my Facebook page in the video description.